Welcome to the session on metallurgy and material science. So, in this session, we will be discussing two important concepts: the limitations of phase diagram or the limitations of equilibrium diagram we discussed, and in time temperature transformation diagram. So, we are going to discuss these two concepts now. And before that, what's the limitations of equilibrium diagrams or the phase diagram we learned? And we have seen the phase diagrams are very useful and interpreting many informations related to the alloys. And for example, while discussing the phase diagrams, I told you there are three important information we can extract from the phase diagram. One is number of phases present, and the composition of the phases, and the relative amount of phases present. Right. But one of the most serious limitation is there is no information on the structural form and distribution of phases. For example, in the phase diagram, we need another technique to get this. For example, you need a microscopic technique or you need something else to know about the structural form. For example, is it a lamellar phase, spheroid, intergranular films, etc. So that's the first limitation. There is no information, direct information on the structural form and how the phases are distributed. The second limitation is the phase diagrams portray only equilibrium states. Or in other words, the phase diagrams portray only very slow rates, so very slow cooling rates. But this is not true always. For example, if you take some industrial applications, say different process like quenching is involved. For example, especially for the heat treatment of steels, the quenching plays a very important role. So it's a process which is done in the industries. But with the help of this equilibrium diagram, the information related to quenching cannot be obtained. So these are the two important limitations. One is there is no information on the structural form and distribution of phases, and the phase diagrams portray only equilibrium states. And then I will be taking to another important concept called the time temperature transformation diagram. So with the help of this diagram, the above mentioned drawbacks can be to some extent can be overcome. Now what is this time temperature transformation diagram? It's also called Ttt diagram or isothermal transformation diagram. And we know well that the cooling rate or the time that play a very important role in the rate of austenite to pearlite transformation in steels. What type of cooling rate is applied? And if you look at the image in this slide, you can see what does it shows is the temperature dependence of pearlite transformation of eutectoid steel. When I say pearlite transformation means the austenite to pearlite transformation. That point you should remember. So that is a point you need to extract from this when I say the pearlite transformation. Austenite to pearlite transformation. We know that occurs at eutectoid temperature, isn't it? If you remember the iron carbon equilibrium diagram, you know that the transformation occurs at eutectoid temperature. Which transformation? Austenite to pearlite transformation. Okay, here you can see two images. One is a top image where the percentage transformation in the top one, and the bottom one the temperature dependence of pearlite transformation of eutectoid steel. And let us see how we can plot this curve. After that we can come to the what does each the curve means. And in order to plot this curve, we take a number of specimens. Say, as you can see in this image, let us take say 4 specimens. Now what we will do, and we heat each specimen to austenitic temperature range. So if it's an iron carbon alloy, now we know that what is an austenitic temperature range. Let us carry out all these discussions based on the steels, because I told you the engineering materials, among engineering materials, the steel and cast iron is one of the widely used materials. So we take 4 specimens, and all these specimens heated to austenitic temperature range. What is austenitic temperature range? It's nothing but the eutectic temperature. It's around, you know that. Okay, so we heat to that austenitic temperature range, and then what we will do thereafter, each sample or each specimen I rapidly transferring one by one to a liquid salt bath of a particular temperature, say 650 degrees Celsius. That you can see in the lower image. It's a liquid salt bath. You can see this is specimen 1, specimen 2, similarly specimen 3, specimen 4. After heating it to austenitic temperature range, I rapidly transfer one by one to a liquid salt bath of a particular temperature. Here say the temperature 650 degrees Celsius. And okay, sorry, yeah. So now keeping each specimen at this temperature for various periods of time. Say this is specimen 1, specimen 2. See, we have taken 4 specimens. Say specimen 1 is keeping at this temperature or the liquid salt bath at say 10 minutes, specimen 2 20 minutes, specimen 3 30 minutes, specimen for 1 hour. I mean, keeping each specimen at this temperature for various periods of time. Thereafter, it is quenched to room temperature. I hope you understand the procedure now. So we take 4 specimens, heated each specimen to austenitic temperature range, and thereafter each specimen is rapidly transferred to a liquid salt bath having temperature say 650 degrees Celsius, and then I keep each specimen at that temperature for various periods of time, and thereafter I quenched it to room temperature. I hope you understand the procedure now. Okay, now a curve is plotted based on this information. Okay, now before that I have 4 specimens now. Okay, so I quenched it to room temperature each specimen finally. Now what I will do is I need to find out the micro constituents of each specimen, or what in order to find out the micro constituents of each specimen, what I will do, I need to do the chemical analysis. Say something called, I told you in the class, EDS is one of the famous technique, energy dispersive spectroscopy. You can find out the chemical composition. So each specimen, the constituents present will be different, because there is a slight change in the processing parameters. So I need to find out the micro constituents of each specimens. So why in order to determine the amount of austenite to pearlite transformation. So the presence of this micro constituents is an indication of the we will give an indication of the pearlite transformation. So I did this procedure. Thereafter I need to find out the micro constituents of each specimen to determine the amount of austenite transformed isothermally at that particular temperature. Then what I will do based on this information, a curve is plotted to show the austenite transformed corresponding to various periods of time. So the specimen 10 minutes, 20 minutes, 30 minutes, 1 hour, you know that now. So based on this procedure, so I will plot a curve to show the amount of austenite transformed for specimen 1, amount of austenite transformed for specimen 2, 3, 4, etc. So that curve indicates all this information. Let us see. So this is what I told you. Once the quenching is over, I will do a chemical analysis is performed to analyze the microconstituents of this specimen to determine the amount of austenite transformed isothermally at that particular temperature. Then plot the curve for various periods of time, and that resultant curve is known as isothermal transformation curve at 650 degrees Celsius. Now, why I called isothermal transformation curve at 650 degrees Celsius? Because soon after I heated it to austenitic temperature range, I told you to rapidly transfer each specimen to a liquid salt bath of a particular temperature, say 650 degrees Celsius. And if it is 700 degrees Celsius, I will call the resultant curve obtained is isothermal curve transformation curve at 700. Similarly, for the other temperatures. Now let us see, this is a curve. Now look at the bottom one. Look at the bottom one. I will tell you one by one, don't worry. So before that, so as I told you, the isothermal transformation curve corresponding to different temperatures like 680, 700, etc. can be constructed using the same procedure mentioned before. So the information obtained from these curves are compiled. The information obtained from the curves are then compiled, means the information obtained from the isothermal transformation curve at 650, isothermal transformation curve at 680, isothermal transformation curve at 700, etc. are compiled to obtain the isothermal transformation diagram. I mean the diagram shown in this image. Now this diagram is called time temperature transformation diagram or Ttt diagram. So this curve is called a time temperature transformation diagram or Ttt diagram. Now see here, if you look at this curve, you can see, if you look at the bottom one, you can see that there is a solid curve on the left side, there is a solid curve on the right side, and there is a dashed curve in the middle, isn't it? These three information you can see, and you can see the temperature here. Okay, so this is the eutectode temperature at which the transformation happens. Above the eutectode temperature the austenite is stable, below the eutectode temperature this austenite is unstable. So this is a temperature, this is a time. Okay, so there is a solid curve on the left, you can see the solid curve on the right and the dashed curve. So what each represents, let us see. The solid curve on the left side represents, I mean the PS, which represents the time required at each temperature to begin the transformation. So pearlite transformation begin curves, PS. The solid curve on the left side represents the time required at each temperature to begin the transformation to pearlite. Okay, and if you look at the other solid curve, PF. So PS means P start, pearlite transformation starts. PF means pearlite transformation finishes. Okay, so it indicating the time needed to finish the pearlite transformation, that is 100% pearlite, and this dashed line definitely represents the 50% transformation completed. Okay, so that is what this curves represents. Now you can also see the eutectode temperature. So a horizontal dashed line you can see here. So above which you can see the austenite phase exists, and below which the austenite is transformed. That is why it is written as unstable. Now what we need to do if the pearlite transformation to occur, the alloy, for example the FEC alloy, has to super cooled below this temperature, I mean the eutectode temperature, then only the transformation to pearlite occurs. So the time needed to commence this transformation depends upon the temperature. And if you look at the curves, you can see that look at the start, pearlite transformation start curve. And look at the pearlite transformation finish curve. Both start and finish curves are nearly parallel, and that will never meet the eutectoid line. You can see it here. The pearlite transformation start and the pearlite transformation finish curves, and if you look at this you can see that it's parallel and it never meet at the eutectoid temperature line. So we can also say another information from this diagram. Towards the left of PS curve you can see the unstable austenite, and the pearlite exists only to the right of PF curve. Okay, so here only the pearlite exists, and here the austenite transformed but not to pearlite. It's something else. Okay, in between PS and PF, both austenite and pearlite present, because it's partially transformed, isn't it? So that is what is this curve shows. Okay. And again, a few other information I can share with you. When the transformation takes place at temperature just below the eutectoid, then what you can obtain, you will get coarse pearlite, which means thicker layers of ferrite and cementite are observed in the microstructure and is called the coarse pearlite. When the transformation takes place at temperature just below the eutectoid. And as the temperature is reduced, the rate of diffusion also reduces. Then you will get fine pearlite, that is thin layers of ferrite and cementite. So the thin layered structure is generally called as fine pearlite, and if you look at this diagram, it is generally observed around temperature 540 degrees Celsius. So the coarse pearlite is observed around 650 degrees Celsius, which means I told you just below the eutectoid temperature you will get coarse pearlite, but the fine pearlite is observed nearly around 540 degrees Celsius. And then at temperature below this 540 degrees Celsius, what will happen? So this diagram helps in giving information about that. Sorry, the Ttt diagram. So at temperature below 540 degrees Celsius, the austenite transforms into another microconstituent called a bainite. So we have not learned about this new thing. While discussing also iron carbon equilibrium diagram, we learned up to pearlite, isn't it? But if you go below 540 degrees Celsius, another phase gets formed, another microconstituent, you can see bainite. So bainite also contains ferrite and cementite. So we know that the microconstituent is a mixture of two phases, right? So the bainite also contains ferrite and cementite. And how it looks like, it forms as needles or plates and is composed of a ferrite matrix with a needle-like particles of cementite. So the main phase present is ferrite, within which the particles of cementite present. So if you look at the Ttt curve, it can be extended from 540 to 215 degree to represent the transformation to bainite. See, that is what is shown here, the 540 to 215. So this shows the transformation. Look at this curve. Let us say this dashed line here drawn represents the 540 degrees Celsius, above which you can see only pearlite exists, and below which you can see that only bainite exists. From 540 to 215 degree Celsius. Okay, and you can see the curves is a C-shaped. See, you can see it's a C-shaped curve. It's a C-shaped curve. Okay, and you can see this C-shaped curve indicates the transformation from to bainite occurs. So this is the nose. This is the nose of the C-shaped curve. It's generally called a nose of the C-shaped curve. So the bainite formed just below the nose of Ttt curve. I mean this. Okay. of Ttt curve is called upper bainite, and at lower temperatures the lower bainite is formed. So upper bainite and lower bainite, even so within the bainite itself there are two types, upper bainite and lower bainite. The bainite formed just below this nose or this temperature range is called upper bainite, and it is also called a fine bainite. Okay, so the upper bainite. So because the microstructure of this upper bainite has a feathery appearance. So feathery appearance. At low temperatures, the cementate grains becomes too fine and an acicular or needle-like pattern is observed, and that is called a lower bainite. So the upper bainite has a feathery appearance, lower bainite has a acicular or needle-like pattern. So as a result, the lower bainite is also called acicular bainite. Okay, now so what I mentioned is the slow cooling, and if I am doing a rapid cooling from the eutectic temperature, what will happen? So let me again brief what I discussed in the last slide. The curves in the last figure is shaped and has a nose at the point and 540 degrees Celsius where the transformation takes place faster. The bainite formed just below the nose of Ttt curve is called upper bainite, and the microstructure is having a feathery appearance. At lower temperatures, the cementate grains become too fine and an acicular or needle-like pattern is observed. This is lower bainite and is also called acicular bainite. Bainite also exhibit considerable variation in properties depending on the temperature at which it is formed. Now I told you if I am doing a rapid cooling to relatively low temperature, the austenite transforms to another microconstituent called Martensite. This is a very important microconstituent. So we earlier while discussing the n-carbon equilibrium diagram, we thought like only up to pearlite existed. Now we know that from this isothermal transformation diagram there is another two microconstituents, bainite and martensite. Okay, so the martensite is a single phase structure that results from diffusion-less transformation. There's no diffusion because cooling rate is faster to prevent the diffusion of carbon. So it's a single phase structure that results from the diffusion-less transformation. And you cannot, I told you the Martensite doesn't appear in the FEC diagram because it's a non-equilibrium phase, non-equilibrium cooling, quenching. It's a quenching operation. It's a rapidly cooling operation where in the case of equilibrium, FEC diagram, it's an equilibrium diagram where it portrays only equilibrium states or equilibrium cooling we preferred. So here in this diagram we can represent the Martensite transformation. Now if you look at this curve, so that is also indicated below 215. So up to 540 pearlite, 540 to 215 or 220 say bainite, and below if I am rapidly cooling below this temperature, see what I will get martensite. You can here also you can see MS, M50 and M90 indicates. MS indicates the martensite formation starts. M50 indicate 50% of the martensite transformation occurred. M90 indicates 90% martensite transformation occurred. So this transformation is independent of time, but it's a function of the temperature to which the alloy is rapidly cooled or quenched. Up to what temperature? Is it rapidly cooled to 220? Is it rapidly cooled to 150? Is it rapidly cooled to 110? So that it's a function of the temperature to which the alloy is rapidly cooled or quenched. So this type of transformation is called a athermal transformation. This type of transformation is also called a athermal transformation. So with this I am stopping, so I can show you another video on the uses of Ttt diagram.